Bismillahirrahmanirrahim. So looking at question 15, where the reaction is between nitrogen monoxide and oxygen. I think the first part is very straightforward. It wants us to complete the following table based on the order of reaction with respect to each species. Okay, so the power, the number where the concentration is raised to, or the power, is actually your order already. Okay, so nitrogen monoxide is second order and oxygen is first order. The overall order of reaction is basically just the total. You add up the individual order of reaction. So that's just 3. Okay, right. Next, we want to look at the 2 separate experiments are carried out at the same temperature. That's the keyword, same temperature, but different initial concentrations. Okay. First, they want you to calculate the value of the rate constant K. So can you please do that? Rate is equals to K times, using experiment number 1, K would be rate over concentration of NO square, NO2, and then you have to work out the units as well. Okay. For those of you who just joined, we are looking at question 15. So Ashraf and Kaushan. Okay, there is a reason why I highlight that same temperature, because as long as you are using the same reactants and keeping the temperature the same, even though it's a different experiment, you're using different concentration, one thing that stays constant is your rate constant. Okay, so that's why they highlight the temperature of 30 degrees Celsius there. So first, in B part 1, we want to find the rate constant for this experiment, for this equation of the reaction between the nitrogen monoxide and the oxygen. So once we find that rate constant, we can then use the same rate constant to find other information about the second experiment later on. So you should get a value of rate constant 8389 or something around that number. Okay, to work out the units, which I'm sure you all should know how to do it already. The units for rate is mole per dm cube per second. If you don't remember, try to look out from the question. Sometimes, most times, it is written there for you. So the units of rate is mole per dm cube per second. The units of concentration is mole per dm cube square and mole per dm cube, and then they cancel out. You bring that bottom term up to become mole minus 2, dm plus 6 as minus 1. You all okay with this? Okay. Calculate the value of NO in experiment 2. So there's a missing information there. You will use the same rate equation. And this time your rate constant is the same. For experiment 1 and 2, because same temperature. Okay, so I will let you work that out. And I will give you the numerical answer shortly. Hello, Hannah. I just realized that you are your camera is on. Mei Ling, we are looking at question 15. Okay, you should get a numerical answer of the concentration of nitrogen monoxide to be 0.000120 or equivalent to 1.20 times 10 to the power of minus 3. The units is of course in mole per dm cube because we are looking for the concentration. I will obviously skip that definition question. If you are done with this part, you can start reading the next part. This next part is the type of question where sometimes students always tell me that it's not worth the time, okay? Because this question wants us to write down the mechanism. They give us the equation and we are expected to write down the mechanism. We try to break down the overall equation into two-step mechanism, okay? Of course, also with the help of the rate equation. Hello, Ayman, we are looking at question 15 now, okay? 15 part D.
Okay, sorry for being late.
It's okay. Okay, are you done with this part? So Ayman, you can take a screenshot first and then you work this out later yourself, or you can always refer to the video because this video will be uploaded on YouTube anyway. Okay, Ayman, already screenshot? Okay, right. Now we move on to part D of question 15. So we are given the reaction of persulfate ion. So persulfate is the peroxo disulfate, S2O8, 2 minus, reacting with iodide ions to form 2 sulfate and 1 iodine. And this is a reaction in the absence of catalyst, because if you remember in the previous topic, we learned that we add Fe2 plus and Fe3 plus to aid in this reaction because persulfate and iodide are both negatively charged species, and it's hard to bring them close to each other because they will repel each other. Okay, right. So this is our overall equation. And the rate equation tells us that persulfate and iodide will appear in the mechanism. Okay, so what this rate equation tells us is that S2O8, 2 minus, and I minus will appear in the rate determining step, slow RDS. Okay, since the order is 1, only 1 mole of each appears in RDS. Okay, so let's start. So when suggesting or predicting the mechanisms, you need to use both the rate equation and the overall equation. Okay, so I like to make my first step to be the slow step. Okay, so I will just prepare this first. What's my rate equation is telling me is that my persulfate S2O8 2 minus 1 molecule, since the order is 1, will appear in the rate determining step or the slow step together with 1 mole or 1 molecule of iodide. Okay, this information is from from rate equation. Okay. Next step, I want to have, I don't know what my product is, but I know that my product will need to have either sulfate or iodine. Okay, so let's try iodine first, and I'll tell you why it cannot be iodine. If I say it produces iodine, I cannot balance the number of iodine, so it cannot be iodine. Okay, so it has to be sulfate. All right, so sulfate, however, not both, because if I put 2 sulfate, right, then I would need to balance my iodide. All right, okay, so and balancing iodide means I'm not producing an intermediate. Basically, I want to produce one product and one intermediate. Usually it's like that, right? There's an intermediate in my product. Okay, so I am going to use sulfate, but only one of them. Sorry, I will change. Okay, so only one molecule of sulfate, my product. Okay, you may be asking me, why are we not using 2 iodides when there are actually 2 molecules of iodide? Okay, I must follow the order. The order tells me how many times or how many molecules that species appears in the rate determining step. So that means there's another iodide molecule in the second step later on. Okay, right, so I only produce one sulfate, and the other one will be an intermediate. Produce. Now, how do I predict or guess my intermediate? Basically, I just have to balance the equation. Okay, so on the left side, I've got 2 sulfates. On the right side, I've only got 1, so I need another 1. Okay, on the left side, I've got 8 oxygens. So on the right side, I will need another 4 oxygen. And one more that is not balanced, my iodine, SO4I. Okay, now an intermediate is usually species that you have not come across before. Okay, so does SO4I exist or not? That's a different story, right? But what's most important for you is that your step 1, the equation is balanced. Okay, another thing that's not balanced is the charge. If you look at the charge on the left side, -2, -1, that's a total of -3. So you've got -2 here. That means your intermediate is negatively charged, -1. Okay. As with intermediate, if it's produced, it has to be immediately consumed. Intermediate consumed. It needs to be really small. So intermediate consumed, SO4I minus. Your step 2 is where you are going to tidy things up. What do I mean by tidy things up? You have to make sure that all your reactants will give the same number of reactants in the overall equation. Okay, so let's see. In the overall equation, we've got 1 per sulfate ion. We've got 1 per sulfate ion, done. Okay. We've got 2 iodide ions. We've only got 1 iodide ion so far in step 1. So that means we need another iodide ion so that they add up to become 2 mole. Okay. Next, products. We have only got 1 sulfate so far. We want 2 moles or 2 molecules. So we need another sulfate, SO4 2 minus. Done. Do we have iodine so far in our products of step 1, step 2? No iodine so far, so I need to add iodine. Okay, before I say I'm done, I need to check again my equation. They need to be balanced. Sulfur, balance. Oxygen, balance. Iodine, 2 of them, and 2 iodine, balance. Charges, -1, -1 to become -2. And you've also got -2 on the right side. Okay, to check if our mechanism is correct, we will add step 1 plus step 2. Okay, so for those of you who cannot see it, you can do this, write it all down. For those of you who can see, the SO4 minus will cancel out. Okay, so S2O8 2 minus plus iodide plus SO4 minus plus iodide to form SO4 2 minus plus SO4I minus plus SO4 2 minus plus I2. Okay, and then you cancel out your sorry, I'm missing something here. I'm missing my intermediate. Plus SO4I minus. Okay, so my SO4 minus will cancel out. 1, 2, 3, 4. 1, 2, 3. Sorry. That is a typo. I did have it, but SO4I minus. Oh gosh, what a disaster. I minus. Okay, so I will tidy them up. SO4 minus, cancel out. My I minus becomes 2I minus. My SO4 2 minus becomes 2 SO4 2 minus and iodine. And they will give me the same chemical equation. Yeah. So if you can see quickly how to write down the mechanisms, you answer this question in the exam. But if it takes you like 10 minutes, please don't. Okay. Even 5 minutes is already too long for me. So if you can see it quickly, do it. If not, then skip it first, right? Because it's not something that's easy to see. You need to, as I said, it's like a jigsaw puzzle. So you need to try to fit all the information together. Okay. Fabian, we are now doing question 15. Right, after you're done with this D part 1, we'll move on to D part 2. I'll let you copy this down first for those of you who did not manage to copy down just now or to write down just now. Okay, next part. A large excess of persulfate ions is mixed with iodide ions. Immediately after mixing, the concentration of iodide is 0.00780. Immediately after mixing is at T equals to 0, just after you mix. Okay, so that means this is the initial concentration of iodide. Under the conditions used, the half-life of iodide is 48 seconds. calculate the iodide ion concentration 192 seconds later. Okay, so this means that after the reaction has gone for 192 seconds, you want to know the concentration of the iodide ion. Now, the persulfate ions is in excess, so it will be constant, and we're not interested in the concentration of the persulfate ions anyway. But what I do want to relate is the time after the reaction has started, and how many times of the half-life is that. Okay, so 192 seconds, I want to know how many half-life that is. Okay, if it's a nice whole number, then we can use this information about half-life, half the concentration. Okay, so and it turns out 192 seconds, if you divide it by 48, this is equals to 4 times of successive half-life. Okay, what I mean by that, you go from 48 and then to 96 and then to 144 and then to 192. Okay, so with that information, we can find the concentration of the iodide after 4 times half-life. Okay, so let's see. Initially, you will start with 0.00780, and then you will go half of that, which is 0.00390. That's only the first half-life. Okay, that's the first half. The second successive half-life, you need to continue to divide that number by half, by 2, 0.00195. That's your second half-life. Your third half-life would be 0.000975. And your last and final, the fourth half-life, which is what the question is asking for, is 0.000244, which is also equivalent to 2.4. Am I doing it correctly? Wait, something is wrong. 0.000975 divided by 2 is, yeah, how did I get that number? Maybe it's, okay. It should be 0.000488, okay, or the same as 4.8 times 10 to the power of -4. So 0.00780 is the concentration at times t equals to 0. My first half-life is 48. The another half-life is 48 plus 48, which is 96. The next half-life is 144. And then 144 plus 48 is 192. So each of these section is our half-life. Okay, so T half of 1, T half of 2, T half of 3, and T half of 4. So the question is, what is the concentration after 192 seconds? And that is the answer, 0.000488 or 4.8 times 10 to the power 4.88. Okay, so the answer is 4.88 times 10 to the power of -4. Now you have to make sure also that iodide is first order, so we know that the half-life is constant. Okay, half-life is constant because yeah, iodide is first order. Another way of doing this quickly is you take the initial concentration, you divide it by half, but you raise it to the power of 4. Okay. If you try to divide 0.0078 divide by 4, because you say, oh, four times the half-life, so I divide it by 4. That is wrong. Okay. You need to divide it by half since it's half-life, but 4 times. You raise to the power of 4. It's the same as dividing by 2, dividing by 2 again, dividing by 2 again, and dividing by 2 again. Okay, for 4 times. Okay, so that's the first time I've seen this style or format of question. Okay. After you're done with this, I would like to go back to question 3. Okay, you done with this? I'll move on to question 3. Okay, so question 3, hydrogen with nitrogen monoxide to form water and nitrogen, and then the results are given to you. This time, however, I want to point out, instead of using concentration in mole per dm cube, we are using partial pressure. Okay, and partial pressure or pressure in general is the same as concentration, but it's for gases. Okay, so we treat partial pressure, it's like concentration for gases. Concentration can spell for gases. Okay, so we're going to find the order quickly because I'm pretty sure that you are already expert in finding the order. Okay, so for hydrogen, we can use experiment 1 and 3. Can you see that in experiment 1 and 3, the partial pressure or the concentration, I will use the term concentration, but it's actually partial pressure because I'm used to that already. So the concentration of the nitrogen monoxide is the same, but the concentration of the hydrogen is different. Okay, so we are going to use experiment 1 and experiment 3. So always take the bigger number. Sorry, 1,6. Nitrogen monoxide, no change. Okay, so take the bigger number divided by the smaller number, and that is an increase in 2. The rate 1.5 times 10 to the power of minus 7 divided by 7.5 times 10 to the power of minus 8. Okay, so that's also an increase in 2, right? So you can quickly say, so if you're already expert, you don't need the long working. So we will say experiment 1 and 3. Okay, the partial pressure of hydrogen increases by 2 or a factor of 2. The rate increases by 2 times. Should we say by 2 times? Because if we say by 2, it sounds like it goes up by 2 units. So by 2 times, okay? Therefore, H2 is first order, straight to the point, okay? You need to show the effect and then only you come up with the order. Okay, so that's hydrogen. I now want to look at nitrogen monoxide. So nitrogen monoxide, I will take experiment 1 and 2. Because experiment 1 and 2, the concentration or the partial pressure of hydrogen is constant, only NO is changing. Okay. Okay, let's see. So I'm using red now. No change to our hydrogen, so I'll just leave it alone. 1.6 divided by 0.8 is times 2. And the rate, I'll use this side. Take the top number, divide by the smaller number. That's times 4. Did you all manage to get that? Concentration of NO or partial pressure of NO increases by 2 times. The initial rate increases by 4 times. Now, if you don't already notice, it is the square of 2. Okay, so that means they are not directly proportional, but they are only directly proportional for the square of the concentration. So this means that it is second order. So looking at experiment 1 and 2, oh, that looks like 7. The partial pressure of NO, okay, partial pressure of NO increases by 2 times. The rate increases by 4 times. Therefore, NO is second order. That's all. For how many marks? No, this is for 2 marks. 1 mark for each, which is easy mark, I think. Okay. Next, write down the rate equation and the units. Okay, so I want to work out the units because it's not in the common units that we are given. It's not something that you cannot do. I'm pretty sure you can do, but I guess it's worth practicing. Okay, so part 2, write down the rate equation. So rate is equals to K times by the partial pressure of hydrogen, which is 1, times by the partial pressure of nitrogen monoxide, which is or second order, so we square it. Okay, they want us to work out. Oh, we don't have to work out, we just have to write down the units, right? Oh, okay, right. So I thought we have to work out the K. So to work out the units, we rearrange. K is equals to rate over partial pressure square. So the unit of rate, if you did not know, again, I say to look at the information in the question. Okay, we don't use mole per dm cube, we use ATM. We can also use Pascal. We can also use grams per dm cube. It doesn't matter what the unit is, but the method of finding the unit is the same. So ATM S minus over ATM times by ATM square. So cancel out. We bring up the ATM. So it becomes ATM minus 2 minus S minus 1. S minus pun okay. Okay. Oh, I just realized that's the balik. Minus 2. Right. Next question. The following mechanism has been put forward. Show how the overall stoichiometry equation can be derived from the 3 equations for the individual steps given below. So how this mechanism, this is called mechanism, relates to the overall stoichiometric equation, or we just call this the overall equation. But if you're wondering what that stoichiometric is the mole ratio. Okay, so how do we relate the mechanisms to the overall equation? We just add our step 1, 2, and 3, and we literally just show it. So part 3, we add step 1, NO plus NO plus H2 plus O plus H2 plus N2O. You add up all your reactants on the same side and all your products on the same side. N2O plus oxygen plus H2O plus N2 plus H2O. Okay. Anything that cancels out is your intermediate. So it looks like oxygen atom is your intermediate here. What else? N2O is also an intermediate because it doesn't appear in your overall equation. Okay, so tidy this up. We've got 2NO plus 2H2 to form. You've got 2H2O plus 1N2. There you go. You get your from mechanisms to the overall equation. Okay. Last question would be suggest which one of the 3 steps is your slow rate determining step. Okay. So to know our rate determining step, we need the rate equation. Copy. So I'll just put it here. Okay. Now, in your rate equation suggests that our slow step must contain hydrogen and nitrogen monoxide. Okay, so look at step 1. Please do not always think step 1 is the slow rate determining step. Okay, it can be the second step or it can even be the last step. Okay, so if you look at the first step, we've only got 2 nitrogen monoxide, which aligns with our rate equation, but hydrogen is not included. Okay, so it cannot be step 1 because there's no hydrogen in step 1. What about step 2? Let's see. If step 2 is our slow step, the rate equation would look like this. P of hydrogen times P of oxygen atom. oxygen atom is an intermediate, so it cannot appear in the rate equation. But we know that oxygen atom is made from 2 molecules of nitrogen monoxide. Okay, so it's made up of NO times by NO. So actually K is equals to partial pressure of hydrogen times by the partial pressure of NO square. So that means step 2 must be the slow step. You cannot also say step 1 and step 2 because slow step is usually only 1 out of 3 or 1 out of 4, 1 out of 2. So no matter how many steps your mechanisms are, there can only be one rate determining step. Okay, only one slow RDS in a mechanism. Okay, so how do we explain this? So we will say step 2 is the rate determining step since it contains hydrogen and oxygen atom, which is formed from NO. Okay, so it agrees with the rate equation. Okay, so I will try to zoom that out. Don't know if you can see. Okay, step 1 cannot be it because there's no hydrogen. And then you move on to step 2. Okay,